Okay, we have the question, can this vector, x1, x2, x3, ignore me, this word, because you're already ahead of this. Okay, x1, x2, x3, this is for everybody else. Can this be expressed as a linear combination of the vectors in this set? Is the question. And this is just any arbitrary x1, x2, x3. So what's the first thing you got to do? Well, you might need to translate this phrase, linear combination of the vectors here. What's a linear combination of these vectors? Well, it's a sum of multiples. The linear combination is a sum of multiples. So we have to write a sum of multiples of these vectors. Now, multiply by what? Well, that's what we got to figure out, isn't it? So the sum of multiples of these vectors we write as C1 times 1, 0, 1 plus C2 times 0, negative 1, 1 plus C3 times 1, 1, 1 plus C4 times 2, 1, 0. Okay? That's your linear combination. And then can this be expressed as a linear combination? That means, could this be equal to x1, x2, x3 for some constant C1 through C4? Now we don't know what x1, x2, x3 are, so we're not going to be able to explicitly, well, we can solve for C1, C2, C3, C4 in terms of the expressions, x1, x2, and x3. How do we do that? Well, use the multiplication property for vectors. And clearly C1 times 1, 0, 1 equals C1, 0, C1. And then we get 0, negative C2, C2. Multiplying this, and C3 times this gives us C3, C3, C3. And here we get 2C4, C4, 0 equals x1, x2, x3. Now you might be tempted to go ahead and write this as a matrix equation, which you usually could. Okay? Or an augmented matrix that corresponds to the system. But I want to write out the actual system. I don't want to make jumps in those steps until we're sure that we see the equivalency between different ways of writing this down. So this becomes just then the vector C1 plus 0 plus C3 plus 2C4, okay, adding the first row, and then negative C2 plus C3 plus C4, and then C1 plus C2 plus C3 equals x1, x2, x3. And then we can write this out as a system of equations. Now, everybody's at a point in this course where you can see what the next step is going to be. You can skip steps. I think maybe, at least for a couple of problems in any set, you remind yourself of what's going on by writing it out thoroughly so you don't lose track of what things mean. Okay? So you have C1 plus C3 plus 2C4 equals x1, because of course these two vectors are equal if and only if the corresponding entries are equal. Okay? And negative C2 plus C3 plus C4 equals x2. And then C1 plus C2 plus C3 equals x3. Now at this stage we can start adding multiples of rows. Okay? We could add this row to this, add a negative multiple of this row, negative 1 times this row to this row, we'll eliminate C1, right? And then C2 will be fairly easy to eliminate. Okay? And so forth. So we can do the elimination, but we're not actually going to do that because I hope we're familiar with how row reduction of the augmented matrix is totally equivalent. So we're going to have the matrix C1, C2, 2. It's not C1, C2, it's 1, 0, 1, 2. 0, negative 1, 1, 1, 1, 1, 1, 0, augmented by x1, x2, x3, and we can reduce that matrix. And then we can predict what might happen, okay? If we end up with a row of zeros and something over here that's not zero, we know that there's no solution, so we're not going to be able to find a C1, C2, C3, and C4 that gives us this. Okay, that adds up to the x1, x2, x3. Unless the whole row is zeros. If we've got zeros here and nothing else here, that means x3 has to be 0. Okay, or whatever is over here has to be 0. And we can't assume that because x1, x2, and x3 could be anything. And whatever we end up with over here is a combination of x1, x2, and x3. Okay? That combination doesn't have to be 0. So if we have a row of zeros equals some combination of these, we know there's no solution. Okay? Well, on the other hand, we could end up with an identity here. And then this row would, or this column would not have to be zeros. Okay? This column could end up with something else, and will, because we're going to be able to reduce this. Okay? Meaning we've got a free variable over here, with C4. So we don't need C4. We can let C4 be 0, and we'd still have a solution. Okay? And that would tell us we don't need all 4 vectors. Tell us we don't need this value. Tell us if we just had this set without that vector, we could still solve it. Okay? Okay, well, we can go ahead and do the reduction. Have you done that?
I began on it.
Okay. Well, go ahead and finish up the reduction, see what you get. I'll do it too, and then when you tell me I'm wrong, we'll use yours.